Right now, the artificial intelligence industry is crashing into a physical wall, and that wall is the power grid. Many Neocloud developers are operating on magical thinking, treating a utility load letter as a guarantee of energized capacity. In reality, a letter indicating potential power in the future is a far cry from a firm, deliverable connection to the grid today. When hardware cycles move faster than utility upgrades, capital committed to these remote, unfinished campuses sits idle, tied to physical structures that cannot yet perform work. AI infrastructure requirements have split along a clear fault line, separating the physical needs of model creation from the needs of model deployment. Training remains a centralized, power-led workload. It requires massive, contiguous blocks of electricity to run campus-scale clusters, making it highly vulnerable to these localized grid constraints. Inference is different. This is the deployment phase, where a model processes a request from a user, an application, or a device. This is where AI generates its response and its revenue. To protect that revenue, the infrastructure strategy must pivot. The focus shifts from the hoarding of centralized compute to the mechanics of decentralized delivery. Training a model can happen anywhere with enough power, but once that model is in production, geographical distance to the end user becomes a critical economic variable. Profitable inference requires ultra-low latency, jitter control, and immediate proximity to the user. Achieving this requires model serving to happen at the network edge, rather than a distant regional hub. While internal AI clusters communicate at terabit speeds, the wide-area telecom networks used to deliver those outputs to the real world operate at a much higher cost and lower performance profile. This gap creates a physical bottleneck. A centralized data center, often located where power was cheapest, is separated from the actual hubs of inference demand by long, high-latency network paths. Real-time AI services cannot survive that delay. Voice agents, robotics, and industrial automation require a round-trip time that traditional long-haul fiber routes cannot reliably provide. Improving a distant server does not fix a geographical network problem. The requirement is not for larger, centralized facilities, but for a smarter, distributed distribution web. At global scale, AI inference functions as an intelligent content delivery network. The current market is crowded with neoclouds that finance and rent bare metal GPUs to developers by the hour. This model faces immediate downward pressure. It is capital-intensive, hardware depreciates with every release, and margins are highly compressed. Hunter Newby's vision offers an alternative. He argues that durable value in digital infrastructure lies in neutral interconnection points rather than raw server space. This concept mirrors the history of carrier hotels, neutral buildings where fiber providers, telcos, and ISPs physically converge to exchange traffic without paying expensive transit fees. Newby is replicating this Meet Me Room model in roughly 125 underserved Tier 3 U.S. cities, targeting markets that have significant economic demand but lack a neutral exchange. Establishing a neutral exchange in these cities aggregates local network demand and generates a local hub of network gravity difficult to replicate. The most durable moat in the AI economy is not the ownership of the fastest chip, but the ownership of the network meeting places where distributed models, telcos, and enterprises connect. This brings us to a strategic partnership between two digital alpha portfolio companies, Qwilt and PacketFabric. Qwilt operates as a federated edge cloud, deeply embedded inside service provider access networks. Qwilt utilizes an open caching architecture that aligns the financial interests of the ISP with the delivery platform, allowing the service provider to host infrastructure while sharing in the delivery revenue. Using hardware like these Cisco servers, Qwilt places cloud-managed delivery nodes inside the service provider's own network, often within miles of the end user. PacketFabric provides the programmable middle mile, creating the high-capacity paths that link enterprise data centers to this edge. With a 65 terabit private network, PacketFabric lets enterprises bypass the public internet using API-driven virtual circuits that provide secure, predictable data movement. By linking this private backbone directly into localized ISP edge nodes, we create a unified path for AI workloads. This open-edge AI fabric is the only architecture capable of moving sensitive enterprise data to a local inference node without touching the public web. Managing this footprint requires operational discipline. We cannot treat a deep-edge network closet the same as a massive regional data center. Next-generation systems like the NVIDIA GB300 require specialized power, cooling, and network switching that dictate exactly where they can safely be installed. This forces a tiered hardware strategy. Tier 0 nodes stay deep in the ISP network, reserved for lightweight API routing and caching where space is limited. Tier 1, the Metro AI Edge, places inference servers in regional hubs to handle real-time tasks like voice agents and video analytics for local populations. Tier 2, the regional AI factories, host the massive GB300 racks in carrier-neutral facilities connected by packet fabric for high-density batch inference and model training. This concentric map visualizes the distribution of compute power, ensuring that high-density hardware is only placed where site conditions allow for it. This tiered architecture protects the balance sheet by ensuring expensive GPU capital is only deployed where power is firm and utilization is high. The commercial goal is to pivot away from selling GPU hours and toward selling outcome-based private edge AI delivery. One primary use case is private enterprise RAG, where a model retrieves sensitive, proprietary data to answer a query. Regulated enterprises will pay a premium to route these sensitive queries through a private virtual circuit to a trusted metro node, keeping their data off the public internet entirely. We can also address the media AI edge, utilizing Qwilt's existing video streaming footprint for live sports clipping and personalized ad generation in real time. This dashboard shows the unit economics. A single AI transaction generates a transport fee for the middle mile, an edge routing fee for the last mile, and a premium inference fee for the compute itself. By packaging transport, routing, and compute into a single service-level agreement, the company transforms from a hardware renter into a high-margin enterprise service provider. The first battle of the AI boom was securing chips. The second was securing power. The third and final battleground is establishing the delivery architecture that makes AI economically functional for the end user. The Open Edge AI fabric functions as a distributed network for real-time intelligence, caching model outputs and moving data predictably across geography. It is an intelligent delivery layer for real-time computation, operating entirely outside the risks and congestion of the public internet. This interconnected fabric avoids the risks of isolated, monolithic data centers that are currently waiting on power grids that may not arrive for years. By merging Qwilt's last-mile proximity with Packet Fabric's middle-mile transport, the result is more than a network. It is the physical control plane for the